Welcome to This Explainer. I am absolutely thrilled you're joining us today because, well, we're tackling one of the most fascinating technological leaps of our entire lifetime. If you've ever typed a prompt into a tool like ChatGPT, Claude, or Gemini, you have probably experienced that brief moment of pure magic. You know the one, you ask it a super complex question and it fires back this incredibly articulate, nuanced answer that makes it feel like there's a real, thinking brain sitting just on the other side of your screen. But today we're going on a little journey to pull back the curtain. We're going to uncover the hidden math and, frankly, the totally fascinating architecture behind that illusion.
Because it's the most natural thing in the world to wonder, right? How does the machine actually understand you? When you ask an AI to, say, write a heartfelt poem about your dog, or to debug a totally messy block of computer code, it really seems to comprehend your thoughts, your context, and your exact intent perfectly. So how does a machine, which is literally just composed of silicon chips and electrical currents, actually process human language?
Well, here is the absolute wild part. It doesn't understand you, not even a little bit. Now, I know that kind of shatters the illusion right out of the gate, but it is the absolute truth. These incredibly sophisticated AI tools are, at their core, essentially just giant math-driven autocomplete machines. They don't actually know facts, they don't have spontaneous thoughts, and they don't even understand the meaning of the words they're saying to you. They are simply calculating the statistical probability of what the very next word should be in a sequence, and they just do that over and over and over again.
Okay, let's dive right into this. Section 1. The Giant Prediction Machine.
Now, this kind of tech didn't just happen overnight. For literally decades, researchers have been trying to figure out how to model text. Way back in 1997, we saw the introduction of something called LSTMs, which stands for Long Short-Term Memory. Those were a type of recurrent neural network, or RNN. But the massive paradigm shift, the real game changer, happened in 2017 when researchers at Google published a landmark paper called Attention is All You Need. That single paper introduced a groundbreaking architecture that just changed everything. Fast forward to 2020, OpenAI releases GPT-3 with a staggering 175 billion parameters. And by 2026, we have reached this massive, totally unprecedented scale of generative AI models.
So what was that 2017 breakthrough? It's called the transformer. The original paper defines it as a neural network architecture that completely ditches sequential recurrence. Instead, it relies entirely on something called an attention mechanism. Honestly, if there is one single thing you take away from our explainer today, it's that the transformer is the fundamental building block for modern systems like ChatGPT. It is quite literally the engine under the hood.
Now, what's really interesting about comparing these older models to the transformer is how striking the differences are. Older models, like those LSTMs we mentioned, had a major bottleneck. They had to process language sequentially, meaning they had to read one word at a time, straight from the first to the last. It's incredibly slow. But transformers, they process all the words in a sequence in parallel, simultaneously. This massive parallel processing means they train significantly faster and can take full advantage of modern GPU chips. Plus, while those old models would literally forget what happened at the beginning of a long paragraph, transformers absolutely excel at linking distant words together.
Which brings us to Section 2. Turning words into numbers.
Because computers don't natively read English, to feed human language into a machine, we have to use a process called tokenization. We essentially take a huge block of text and chop it up into smaller, bite-sized units called tokens. Now, these can be whole words, fragments of words, or sometimes even single characters. Then, we map each token to a word vector, which is basically just a really long list of numbers. So to an AI, the word cat isn't C-A-T, it's a very specific coordinate point floating out in this vast mathematical space. And words with similar meanings, like dog and cat, well, they end up positioned very close to each other in that space.
But human language is incredibly messy, right? We have the word bank, meaning a financial institution, and the exact same word bank, meaning the side of a river. For you and me, the context makes the meaning completely obvious. But how on earth does a language model figure out which mathematical vector to use? If it just mapped every single instance of the letters B, A, N, K to the exact same list of numbers, the computer would get totally confused.
Well, to solve this ambiguity, the model needs space to think. GPT-3, for example, uses 12,288 dimensions for its word vectors. No, really, 12,288. You can kind of think of all those extra dimensions as this massive scratch space. As the text passes through the model's layers, it uses these dimensions to literally write notes to itself about a word's context, gradually sharpening its understanding of whether you meant a riverbank or a savings bank.
All right, let's get to the really cool stuff. Section 3. The magic of self-attention. This self-attention mechanism is exactly what the transformer introduced, and honestly, it operates exactly like a matchmaking service for words. Here's how it works. Every single word in a sentence creates a query vector, which is kind of like a checklist of characteristics it is looking for in other words. Simultaneously, every word creates a key vector, which is a checklist describing its own characteristics. The network then compares the keys and queries using a dot product. When it finds a really strong match, boom, it pairs those words up and transfers information between them. And this brilliantly illustrates why that matchmaking is absolutely crucial. Just consider the sentence. The customer asked the mechanic to fix his car. Who does the word his refer to? Is it the customer or the mechanic? Through this self-attention matchmaking process, the pronoun his sends out a query looking for a male noun to attach to. The attention layers calculate all the surrounding context, match his with customer, and transfer that specific information right into the vector for his. And just like that, the model successfully resolves the ambiguity.
So how does it learn to do this? Section 4. Training at massive scale.
See, when a model like GPT-3 first starts out, its 175 billion parameters, which are basically just adjustable weights, are set completely at random. Out of the box, it is terrible at predicting words. Training it is a lot like trying to find the perfect shower temperature in a crazy complex plumbing system. You turn a random valve, test the water, and if it's too hot, you adjust it. If it's too cold, you adjust it the other way. In AI, this cycle of predicting, measuring the error using something called a loss function, and then adjusting the weights backwards through the network is called backpropagation and gradient descent. Now, just imagine doing that exact process with 175 billion valves, all simultaneously.
And to get those billions of valves tuned perfectly, you need a staggering amount of data. 70 trillion. Online sources estimate that GPT-5 was trained on more than 70 trillion tokens of text. To put that into perspective for a second, a typical human child encounters roughly 100 million words by the time they're 10 years old. So the secret ingredient to why these simple mathematical functions can suddenly compose essays, translate complex languages, and write computer code is quite simply massive, unprecedented scale.
Let's move to and see how this builds into something we actually use. Section 5. Guiding AI with feedback.
So, how do we build a truly conversational tool out of this raw prediction machine? We use a process called reinforcement learning from human feedback, or RLHF. It goes like this. Step 1. Human knowledge workers write out very natural, accurate responses to various prompts. Step 2. We do supervised fine-tuning, basically comparing the AI's generated answers to those human answers. And finally, step 3, a reward model scores the AI's responses on a scale from 0 to 1, with 1 being the most human-like and helpful. The AI then uses these exact scores to optimize its internal policy, learning over time to choose the responses that will result in the highest possible reward. That is exactly how it learns to chat with you so naturally.
But of course, we have to talk about the downsides. Section 6. Powerful but not perfect.
So the crucial point is that we must understand these limitations. First up, hallucinations. Because the model doesn't actually know facts, it can confidently generate totally false information that sounds highly plausible simply because the words happen to fit the statistical pattern. Second, biases. If the billions of web pages it trained on contain human patterns that are unfair or offensive, the model purely and mechanically amplifies those exact same patterns. And finally, they are incredibly resource-heavy. Training and running these massive networks requires tens of thousands of GPUs and immense amounts of energy.
Which brings us to our final thought today. As these models get larger and larger, learning to seemingly reason, passing rigorous medical exams, and writing flawless code, researchers are genuinely divided. Some argue that by successfully predicting language at this immense scale, the models are actually beginning to develop a true underlying understanding of the world. But others, they insist they are nothing more than stochastic parrots, just highly complex algorithms blindly repeating mathematical patterns of words they've seen before without any real comprehension whatsoever. So the next time you type a prompt and feel that little spark of magic, ask yourself, is there a mind in the machine, or is it just a flawless illusion built on trillions of numbers? Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.